Hello again. We're back with something a little different this time. I decided to try a slightly different style of presentation here. Still going to be working through code, still covering Advent of Code Day 8 in Rust, but adding a little bit more structure to how this is all recorded. If you like this format, or even if you hate it, let me know in the comments. Either way, let's get stuck in. Today we're looking at Day 8, Haunted Wasteland. As always, we're going to be skipping the story behind this. You can read that yourself if you are keen. But here's our input file for today. Starting with part 1, we interpret this file with the following rules. First, the top line of the file contains a pattern of R's and L's. Those represent moving left or right. Then we get a blank line, as you can see, and then we get a collection of junctions. Each junction has a label, which is to the left of the equal sign, and two possible next steps, one left, one right. Together, parsing all these, we form a graph, in the computer science sense, of nodes and edges. Our instructions are to start at the node labeled AAA, and follow the rules, the R and the L, repeating once we get to the end until we end up at the node ZZZ. So that one down the bottom there. Running this through for the sample input file, here's how we would go. We'd start at AAA and we'd move right because that's the first step in the pattern. That takes us to the node CCC. We then move there. Now we need to move left, which in this case would take us to ZZZ. And then we're at ZZZ, so we're done for part 1. We need to return the number of steps it takes us to get from the start point to the end point as the answer for this puzzle. Notably, in this case, if we ended up at ZZZ, regardless of whether we tried to move left or right going forward, we're still ending up at ZZZ, so all future steps would be there, but we've just got to record the first time we hit that endpoint for part 1. So let's take a look at the code for part 1. As a reminder, all code for today and all other days is in a repository linked in the description. So we start by defining a structure to store each one of these nodes. It's a fairly simple structure, just storing a string for the left and the right choice. We also create a small helper function that checks an array of U-sizes. This function is mostly for part 2, but what it's all about is have we found a path to the end and recorded a non-zero length for that, and it returns true or false if we have for that starting point. For part 1, just consider this as a function that returns true or false depending on whether we've reached the end. Looking at the main body of the function, first up we head right to reading into the input file, ready to parse. We initialize an empty hash map for all of our nodes called nodes. Here the key is the left of the equal sign, it's a string, and the value is a node structure containing the right-hand side of the equal sign. We then start splitting up the lines. We read that very first line as the set of instructions. You can see there we grab line 0 and just pop it into a directions variable. Then we take the rest of the lines and we set up a regex. Now this regex parses 3 things from our various node lines. Parses a thing called lock for location, a left and a right. You'll see how we use that in a moment. So next, we then parse through the remaining lines. We loop through them. If we find any empty lines now, we just continue. It's likely due to copy and paste. So we skip any lines that are empty. We then use the regex that we just defined to match the location, the left and the right from each node. We extract those from the string match, store them in our nodes hash map with the location being the key and that node structure being the right, And then we also note the starting points. For part 1, the starting point is just the position AAA, so you can ignore that if statement for the moment. We'll come back to that. But imagine that starters, that vector we defined before, is just the single node AAA. With our instructions parsed and our nodes processed, we now need to make our way from AAA to ZZZ. We use that vector starters to store the current position, the current node that we're up to. For part 1, this vector only ever has one entry in it, and it's hard-coded to the node AAA. We also store a vector of the same length as starters with all zeros in it to keep track of the lengths from the start to the end. For part 1, this is just a single number, so a vector of length 1. We then continue a loop until we've reached the end, and FREQ, or frequency, has a non-zero value in it. We increment the counter C throughout this loop. That's used to keep track of the step that we're up to, and that lets us determine what instruction we need. We get the next instruction, so left or right, from our instruction string using the modulus operator, so that if we've extended beyond the end of the instructions, we loop back around and start from the beginning. Then for each node in our current collection, for part 1, as I said, just one, we follow the directions, left or right. We continue this until we find a node that ends with the letter Z. For part 1, it's just ZZZ, but we store the length of number of steps it took to get there in the frequency table. If we haven't reached the end yet, we just adopt the new left or right node as our new position, increment our counter, and continue on until we find our way to ZZZ. For part A, we then just need to return the length, number of steps it took to go from AAA to ZZZ and print it out. So you could ignore this commented out piece of code, but taking that frequency, the first member of that vector, we get the answer 19637. So that's the number of steps we had to go through to get to the endpoint. And that gives us the answer and our first gold star for part 1. Now let's take a look at part 2 of this problem. So the change for part 2 is that we now need to process multiple journeys in parallel. In particular, we need to find all the nodes that end in the letter A. Each of these represents a starting point. We then need to follow each one step at a time, following the same set of instructions, until all of the nodes that we're tracking happen to be aligned to an exit point. An exit point now is any node that ends in the letter Z. Critically here, all of the paths need to reach the endpoint at the same time to end the function. If only some of the points have reached the end, the process needs to continue until all of them end up at the end at the same time. So let's have a look at where the resulting code changes are to compensate for this change in rules. Looking back at our parsing loop, we now see why we store all of the locations that end with an A in our starters vector. And in this case, we have roughly a dozen starting points that we're going to need to track through one by one. So starters now is a vector of roughly a dozen different initial nodes. Here, looking back at our actual processing loop, we find the first time that any given one of those parallel pathways that we're tracking reaches an endpoint. And we store the number of steps it took to get there. If we've found that number for all of the starting points, we then exit the loop. Now, this is not a universal solution to this kind of problem. The only reason we can do this is because of an important factor in the data that we're analyzing here. So what is that important factor? And that's loops. So for the given input file and set of instructions that we have, all of those starting points, once they reach their respective end nodes, actually loop back to the starting point. So for this to have happened, both the right and left instructions and the series of nodes and which ones they connect to, it needed to be carefully chosen by the people creating this problem. There's a little bit of a hint to this in the way that the sample data for part 2 is explained, where the first path, there's 2 in that case, reaches the endpoint every second step and then loops back to the start and repeats, whereas the second path reaches it every 3 steps. And you can see there, they're not quite in sync, but eventually they will both reach the endpoint. Now, the question is, how do we find, knowing only how long it takes to get there the first time and knowing that there's loops, how do we find the number of steps it's going to take for all of those starting points to end up at their respective endpoints together? Given that we have loops, given that we know those lengths, we can take a shortcut in our calculation. The input file has about a dozen starting points. They take quite a long time to reach their loop. You saw the one before, about 20,000 steps. Given that each one has a slightly different number, if we ran this process until it naturally completed, which we'll see with our final answer at the end, we'd be waiting a really long time. Instead, we make use of a mathematical function called the lowest common multiple. This is a number that gets computed from 2 inputs, and the result of the lowest common multiple of a and b is some number x, where x is the lowest or smallest number of which both a and b are a factor. So to use the example input, we have one that repeats every 2 steps, one that repeats every 3. The lowest number that has both 2 and 3 as a factor is, in this case, 6. If it was 2 and 4, the lowest number would be 4. We make one more adjustment to this because we don't just have 2 numbers that we need to calculate across, we have several values. To do this, we calculate the lowest common multiple of the first 2 elements in our list. Then we calculate, using the result of that, and the third element, the lowest common multiple of those 2 numbers, and so on and so forth until we reach the end of the list. And there's a property of the lowest common multiple that doing that and processing it in that way will give us a number that is the lowest common multiple of all the numbers in the list. So jumping back to our final code snippet, now that we have this array of frequencies, which is the lengths to the first repeating point of all of the different starting points, we then loop through that list, calculate the lowest common multiple with sort of a running total, using an externally implemented lowest common multiple function. You can implement it yourself, but I didn't here. We use a unsigned 128-bit integer because this number gets really, really big. And after we've run through this loop for each of the different starting points, we now get our final answer. As you can see, our final answer here is a truly massive number. If we had taken the naive approach, or the approach we could have gone with for part 1, and just continued that loop until we reach this point naturally, even with an extremely fast computer, this is a lot of iterations to have to go through, and this would have taken us a really, really long time. The way we got to knowing that this was the way to approach it was really about looking at the input function, doing a bit of debugging, and trying to understand what was going on. Initially, when I wrote this, I did just let it run to see how long it would take to reach that point. After it felt like it was a little bit too long, I realized there must be something more going on here. Started to print some of those endpoints and the next step after them as a little bit of debugging, and that ultimately led me to realize that there was this looping behavior, and we had this nice property in our input function that allowed us to take this shortcut. So with all that, that's our second answer for part 2 of day 8. That is the end of what we needed to do to get our 2 gold stars. And I hope you like this new format. Please do let me know. If you did, consider subscribing. I'll be going through all days up to day 18, which is where I ran out of time. But I am Elliot, I build stuff, and I really look forward to catching you in the next one.